Hello, it's stat135, lecture 33. Last time we started chapter 14, doing a matrix approach to regression, including simple linear regression. So we considered matrices y, which was our response variable with n observations, x0, which is just a column vector of ones. X1 is observations of our first predictor variable, up to xk, which is our kth predictor variable. Beta 0 to beta k is a column vector of coefficients, and E1 to En is a column vector of error terms. And x is a n by k plus 1 design matrix. N is greater than or equal to k plus 1, and n has full rank. The standard statistical model is y is x beta plus e, where beta is some unknown coefficients, and e is some unknown error terms. So only Tyche knows those unknowns, and we see some data, and we can make estimates of what beta and e are. That's what we call beta hat and the residual e hat. So beta hat's defined as that vector that minimizes the Euclidean norm of the residual vector, y hat minus y. So y hat minus y is the error, so predicted minus actual values of the response variable. So using some geometric argument, we found that that our estimated coefficients beta hat is x, the transpose of x times x inverse x times y. And today we're going to cover 14.3. For simple regression, we're going to show that beta 1 hat's the covariance of x and y over the variance of x, and beta 0 hat is the expectation of y minus beta 1 hat expectation of x. So you sort of have to find what beta 1 hat is before you find beta 0 hat. We'll do an in-class exercise so you can see how you would apply these ideas in R, and then we'll start to explore statistical properties of beta hat, such as its variance, the variance covariance matrix in section 14.4. So let's see here. We're gonna introduce some random variable notation. So x is a random variable that's uniform on x1 to xn, and y is a random variable that's uniform on y1 to yn. So the expectation of x is just the standard mean of x, and expectation of y is standard mean of y. Variance of x has the usual formula for variance. We have basically two formulas for variance that are equivalent, and covariance has its usual formula as well. So we went over 566 in the book, where we just saw what x transpose x inverse xy means for in simple linear regression. In that case, x transpose x is a 2 by 2 matrix, and noting that the inverse of a, b, c, d is 1 over the determinant times the diagonals get transposed, and the off diagonals are negated. We can see what x transpose x inverse is for us, and then we can see what x transpose x inverse x transpose y is, so that is here. So you can see, first of all, that the determinant is basically n squared, the variance of x. And furthermore, you can also see that that the bottom term right here, you can see that this term right here is n squared covariance of xy. So it's pretty easy to see that beta 1 hat is covariance of xy over variance of x. So that's fine. To show that beta 0 hat is expectation of y minus beta 1 hat expectation of x takes us a little bit of work, where we have to do a little algebra trickery here, but it's really pretty straightforward. So I'll let you read through this and there shouldn't be any problem. So next, I wanted to go through the calculus approach, also called linear least squares, for finding beta hat for the simple linear regression case. To do this more generally, you would need to do calculus in multivariables, which involves gradients and Jacobians and all that good stuff. But I think that geometric argument will suffice for us there. So we'll just do this for k as 1. But anyway, you'll get the flavor of it from this. So what we're trying to minimize is the residuals squared, the sum of the residuals squared. And so we're looking at the difference of yi minus beta 0 minus beta 1 xi, where beta 0 and beta 1 are just are thought of as variables that we're searching for the minimum of them. So so what we're going to do is we're going to set the partials equal to 0, and when we do that, we actually see that we get two what are called normal equations. We see that the sum of the residual is 0, and we see that the sum of xi times the residual is 0. Those will play a role later. But setting those partials equal to 0 and solving, we get beta 0 and beta 1 hat that is what we found before. So then we did an example in class where you got to put these ideas to use to a real simple problem. And so here we have n is 5. We have a scatter diagram of 5 points, which I've drawn here, and we see x bar is 0, y bar is 1, and the covariance of xy over the variance of x is 7 over 10. Beta 0 hat is y bar minus beta 1 hat x bar, which is 1. So we get our regression line 1 plus 7/10 x. And I do know that this is correct because the next thing we're going to do is an in-class exercise where we're going to do exactly this problem in R, and we'll get the same answer. So if you didn't get this answer, then your calculation of the covariance and variance is probably not exactly correct. So in the homework, you'll see another formula for the regression line that's given by normalizing. So it's given by normalizing y hat and x, and involves the correlation coefficient of xy. So you'll explore this in the homework. In R, in class exercise 33 on B courses, a few things here. So notice that LM is R's linear model function. So a parameter it takes is called formula, and you need to put in the order of what's the predictor and response variable. So y is the response, so y tilde x is response predictor, and you get a list. Reg is a list. You can, if you write summary, it'll give you different information. If you look at the coefficients of reg, so reg $ coefficients will give you beta 0 hat and beta 1 hat, and you can use this to predict, for example, what y hat will be when x is 3, using the equation highlighted there. So for example, reg $ coefficients 2 is 0.7 because 0.7 is beta 1 hat. You can plot. Geom smooth allows you to plot the regression line, and setting SE false gives us what we need. And if you say method is LM only, then you'll also get error bars, and we'll talk about those error bars later. So then we briefly talked about the statistical properties of least squared estimates, so introducing the notion of random vector. And so we can talk about the expectation of a random vector and the variance of a random vector. The variance of a random vector is a variance covariance matrix. This is a k, actually it's a k plus 1 by k plus 1 matrix. So then a big important theorem is theorem A and B on page 573, which tells us that the expectation of beta hat is beta. In other words, beta hat's an unbiased estimator of beta, and the expectation of the residual is 0, and the variance of the residual is the diagonal matrix sigma squared. So that's the variance covariance matrix. So, and furthermore, the variance of beta hat is sigma squared x transpose x inverse. So that's your covariance matrix. And so the book proves this using linear algebra machinery, and I don't think it gives any insight into what's really going on. If you're good at linear algebra, then you can read it and understand every line of it. But I think it's a good exercise to actually go through everything for k is 1 and see how that works very concretely. So that's what we're going to do. So we're going to try and understand what the variance of beta hat is. So fortunately your book works that out. So page 574 in Rice, the variance covariance matrix is given for us here. So that's sigma squared times x transpose x inverse. Now x transpose x inverse we worked out on a previous page of these notes. So I think everything here is pretty clear. The variance of beta 0 hat's the 1, 1 term of the matrix, and using some algebra, which I explained below, you can put this in another form that will be useful to us, and that's highlighted in yellow. The variance of beta 1 hat and the covariance of beta 0 hat and beta 1 hat also have useful forms that I've highlighted for you. And the algebra that I indicate here, you can just read on your own. There shouldn't be any question about that. I want to point out that knowing the variance of beta